Okay, in this section or this video we're going to have a look at the reactions of phenylamine and how we turn phenylamine into a variety of organic products. So this covers in your textbook page 217 to 219. The first reaction we're going to look at here is phenylamine with nitrous acid. So not to be confused with nitric acid, guys, which has a formula of HNO3. Nitrous acid is HNO2. It's a very unstable substance, so you'll find that it's made in situ, which means it's made in the place of the reaction. So phenylamine, a black oily liquid formed as a diazonium ion, decomposes immediately due to instability. Now, let's not worry about what a diazonium ion is for the minute, but what we do need to know is that when phenylamine reacts with nitrous acid, we get this black oily liquid. Okay. Now, there's the equation on the screen. So hopefully you all recognize this as our phenylamine. This is the nitrous acid I just spoke about. You should be able to recognize that perhaps. Okay, it's a compound called phenol. And I'd like to just take a wee second and give me some possible observations here. Apart from the black oily liquid being formed, what are the other observations in here? Okay, well, the other observation is that you get colorless and an odorless gas produced, and that gas gives you negative tests. When I mean negative tests, for the squeaky pop test, for the lime water test, for the lit splint test, for the glowing splint test, it gives negative tests for all of those. So it's nitrogen gas. Now, this reaction only applies to phenylamine when it is warmed. I will get a different product when I carry out the reaction of phenylamine with nitrous acid in the cold. We'll look at that in a couple of slides over. Primary aliphatic amines, okay, will react with nitrous acid, and again the main observation is colourless, odourless nitrogen gas, and again we get the alcohol. So wherever the amine group is, okay, we end up with an alcohol group. Now, no matter what conditions I do this one in, whether it's warm or cold, I get the same product. There is no alternate reaction for aliphatic ones in the cold. Aromatic ones, I will get a different product, which, as I said, we'll discuss in a few minutes. Aliphatic ones, doesn't matter whether it's warm or cold, I always get an alcohol. Okay, and that's because these aliphatic amines are very unstable. Okay, we can't stabilize them to form this other product that we're going to talk about. So let's look at diazotization, right? A whole new word for you, but we'll discuss this as we go through the slide. So this is the formation of what we call a diazonium ion, and this comes from our phenylamine. A diazonium ion allows enhanced reactivity under this benzene ring and allows us to start adding things to this benzene ring, which we might not normally be able to do. Okay, so you will need to be able to recognize this as so or as so. Now, what I would tell you is be careful. The benzene ring, okay, is here, of course, going to that bond. This is the positively charged nitrogen, so they comes up in multiple choice questions as to sort of identify which one is the correct structure. So, and they very often they'll just put the positive charge here. Okay, remember it's on the one closest to the benzene ring. So diazotization refers to the conversion of a primary amine to a diazonium group, this being the diazonium group. It only applies for aromatic amines. As we said in the previous slide, aliphatic amines are too unstable and they will just decompose into the alcohol. Okay. So, but this has to be done at less than 10 degrees. So I spoke on the previous slide about doing this reaction with nitrous acid, okay, in the cold, and it has to be less than 10 degrees. It's usually done between sort of 5 degrees, between 5 and 10. Anything below 5 is simply makes the reaction too slow. Alright? Right, so let's see how we actually do this diazotization that we spoke about and make this diazonium group. Okay, so we take our primary aromatic amine, okay, so must be aromatic, so aminobenzene, or as we probably call it more frequently, phenylamine, we use sodium nitrite, and we use excess HCl between 5 and 10 degrees Celsius. And the reason for that is because those are what we use to make our nitrous acid. And as I said earlier, we make our nitrous acid in situ, because very simply, if we leave our nitrous acid around for a while, it will react with oxygen in the air and give us nitric acid. So that's not what we want. We want our nitrous acid. And as I said earlier as well, we do this between 5 and 10 degrees. Simply below 5 degrees, the reaction is too slow. And above 10 degrees, that diazonium product that we're trying to get will decompose. Okay, and it will decompose. If we go back a couple of slides ago, it will decompose to the alcohol, which in this case would be phenol, plus water, which is not a big problem, plus nitrogen gas. And this can cause it to explode, and it has exploded on many occasions, because the nitrogen gas can be made very, very quickly in an enclosed space if you allow this product, this diazonium product, to warm up. So that's why it's it can be very dangerous if you don't control it properly. So there's my phenylamine, my nitrous acid and my excess HCl. There's my new diazonium ion. So if we, my N2 plus, or you could have it written as N triple bond, other N, positive charge there, and then Cl minus, okay, plus your waters. And this, remember, is all happening between 5 degrees and 10 degrees. If this is allowed to warm up above 10 degrees, what happens is that the benzene diazonium ion will react with the water. You'll get phenol, which you don't want, and you'll get possibility of an explosion from the hydrogen gas. Okay, so last slide is not in the specification anymore, so that's why I skipped through it. Right, so you might say, well, what's the point of this diazation? What's the point of making this diazonium ion? Well, this is a phenomenally important step way in making other organic molecules, if you like. Okay, so the one that we're going to look at is the formation of coloured compounds, which are used in the dyeing industry. And this involves coupling of that diazonium ion with phenol. Now, coupling basically means to join two molecules together. Okay, and specifically this one, we're going to look at electrophilic substitution on the number 4 position of the phenol with that diazonium compound that we made on the previous slide. And this time we turn our diazonium ion into what we call an azo compound. So we have another new group. We have C and double bond and single bond C. That's our azo compound. And that I'm going to circle now is what we call an azo group. Okay? So let's have a look. There's my benzene diazonium ion. Okay, if you look, remember to the last slide, we had the benzene diazonium chloride. Okay, this is the phenol. Okay, so this, as you can probably see, because of the positive charge, can act as an electrophile, attacking the delocalized pi bonding system of the benzene ring of phenol. And then we get here now our azo compound, and you can see our azo group there. You can see why it's called an azo group. You can see why it's called coupling, because we've basically joined these two compounds together. Okay, and then we have an H plus. If you did have the Cl negative here, you would have, of course, HCl, but in the blue is just the ionic equation. Okay, so this is the equation, guys, that for coupling, okay, with the benzene diazonium chloride and the phenol here. That's the one that you have to know off by heart. It's the only one in the specification that you have to know without them giving you any help. Other ones, they would have to give you the structure of whatever they were coupling. Okay, the product here, and I'll just clear the screen so you can read the name of the product. This is called 4-hydroxy-phenol azobenzene. So there's your azobenzene, there's your phenol group, there's your position number 4. This is high priority functional group, position number 1, position number 4, and of course that's the azo group there. And it's a very bright yellow dye. It's used extensively in the dyeing industry, food colorings, things like that. Okay. Conditions that you need to know. Phenol is dissolved in sodium hydroxide. The reason for that is to make a compound called sodium phenoxide. Okay, as so. That acts as an intermediate in the reaction, and it's done below 10 degrees Celsius, between 5 and 10. Okay, so a few questions coming up here now that you want to have a go at. Alright, so you can either pause the video or you can do them from your textbook. It's 5.9M. So pause the video again, I'm going to move on. You pause the video again, I'll move on. You pause the video again, I'll move on. This is 5.9M. Okay, so we looked at that one, and that was a yellow coloured dye that was produced, the 4-hydroxyisobenzene. Different dye colours will give us different colours, or sorry, different compounds will give us different colours. So if we look at this one, we have got the core of the molecule is exactly the same as we had in our example. Okay, same again here. But we've added different groups on in the white here, 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 and here. And because of that, we get different colours. Here we have alizarin, a yellow colour. Here we have methyl red. And you probably recognise this, perhaps, as an acid-base indicator that you use in class. And that's where these acid-base indicators get their colour from. Okay, so you can see over here on this side we have a whole stack of different shades and different colours, and that's because we change the group. We keep the majority of the compound exactly the same because this is what helps us get the colour, and then we change these little groups at the ends which give us different shades and different colours. Okay, so we're into 5.9N. You can have a go at this. Right, so what is it that causes this colour? Right, so we need, in order for colour to be apparent, we need conjugation within a molecule, and that means alternating double and single bonds. Now that does not always give us colour. So for example, in benzene, okay, we do not have colour in benzene. Sorry, I've done that in the wrong place there. We do not have colour in benzene, alternating double single bonds. Okay, but we need that at least. What happens when you get alternating double single bonds is that the sigma bonding area and the pi bonding area of the p orbitals, instead of being far apart, they actually become quite close together. Okay, so how does that cause colour? Well, that means that visible light can come in and it can cause the electrons to be promoted from the lower energy level to the higher energy level, and the wavelengths of white or visible light therefore get absorbed. Okay, so this is our visible light coming in, okay, and it's promoting the electrons from lower energy level to higher energy level. Unless you have conjugation, you don't get the energy levels coming closer together, and therefore even here, if I had visible light coming in, okay, so energy from visible light, it isn't enough to promote these electrons from here up to there. That simply doesn't happen. Okay, so I have to have this area of conjugation to start off with. Now the area specifically within a molecule that is responsible for it having light is called a chromophore. Okay, so just like I said up here with benzene, okay, I have got an area of conjugation, but I do not have a chromophore. I don't have an area of double single bonds which can actually give me colour. Okay, so not all conjugated systems are coloured. They must have this chromophore. So if I go back to my dyes over here, I'll just tidy this up a bit. We can see an area of extensive double single bonds alternating the whole way through these molecules. Okay, and the same is true down here. So So those are extensive areas of conjugation, and they are also able to allow electrons to promote the electrons from lower energy levels to higher energy levels, therefore absorbing wavelengths of light from visible light and causing it to colour. Those wavelengths of light that are absorbed from visible light change ever so slightly by me changing these white groups, and that gives me slightly different colours for every single dye. Okay, so here's an example of one here. Okay, you can see alternating double, single, double, single, double, single bonds throughout that structure. This green area is the chromophore. The rest of the molecule just does what the molecule is designed to do. Okay, here we've got vitamin A, which is or beta carotene. Vitamin A, it's a red orange colour. You can see again. Okay, it owes its colour to this chromophore of alternating double, single bonds throughout it. That's what makes your carrots sort of carroty colour, your peppers that colour. Okay, amphotericin B. This is an antifungal drug. It's not designed to be coloured, it just happens to be that the structure ends up having a chromophore being coloured. You can see it, I hope, quite obviously within that structure of the molecule, and it's a pale yellow colour, that amphotericin B. Phenolphthalein, an indicator that you saw. These contain what we call oxychrome. So if we look at phenolphthalein here, now is this phenolphthalein an acid or is this phenolphthalein an alkali here? Well, you have a think about it. But we've got our alternating double, single, double, single, double, single bonds. Okay. This is actually it in acid. And you probably could work that out because you have carboxylic acid group there. If it was an alkali, you wouldn't be able to have that group present. Okay, but you can see there's no alternating double, single bond in this region. So the chromophore, so we have 3 conjugated areas, okay, but we don't have a chromophore. We don't have colour. So when you have phenolphthalein in acid, it's colourless. If I put phenolphthalein into alkali then, I deprotonate acidic groups and I change the bonding a bit. Okay, so you can see here, deprotonated, here, deprotonated, by adding OH minus and deprotonating with the base. Now by alternating this group, I've now extended that area of conjugation. So whereas here, the area of conjugation was broken, if you like, now I've extended it, okay, and it runs throughout the entirety of the molecule. And this is now alkali. And we take advantage of the fact that this oxychrome, so these are the groups that actually cause things to become coloured in different environments, that this oxychrome changes colour when something's in an acidic or alkaline environment. And that's how we use it as a pH indicator. Okay, so you can have a go at that question on the board now, please. That's from exercise 5.9M. So is that one. Pause the video. So is that one, 5.9M also. Okay, so just a very quick bit on properties of these amine salts. So amines are very regularly used in drugs and pharmaceuticals. Okay, and they're very much sold as their salt as opposed to their free base, for the simple reason of as their salt they're ionic, so their solids at room temperature. As their salt they're ionic, so they're very, very soluble. Okay, and you can see the salt groups, the amine salt groups, quite clearly in here. And these are just some over-the-counter medicines that you may have at home. Okay, cocaine's another one of an amine compound. Okay, you can see these are all molecules. Caffeine's another one. Okay, these are all molecules which act on the central nervous system at the minute. Okay, perhaps you've heard of dopamine, serotonin, things that cause depression, or lack of them, sorry, perhaps cause depression. Okay, but these things have great ability to stimulate the central nervous system. Nicotine is another one, exactly. stimulates the central nervous system. You can see amine groups here. Okay, painkillers. Okay, so morphine, codeine, bought over the counter, heroin, all compounds which are used to kill pain as analgesics. So they're working again on the central nervous system. Okay guys, so we shall leave it there. That is a video then on taking us right up to page 220 of your textbook. Okay, so in the amines it's taking us right up to page 220, so you should do that reading and make sure you do the questions as well, and more importantly check those questions, check those answers, make sure you know exactly what you're doing with regards to this topic. You should now be able to get the past paper question booklet and start doing that also guys, so please do that, and again check answers.